All right, so let's start the third case where we have a system of differential equations, but we get complex eigenvalues. Now, I'm not going to teach you how to solve a full differential equation problem in this video. That means I'm not going to teach you how to write the final solution, but we have to learn how to find eigenvectors when you have complex eigenvalues. Okay, so that can be little bit different because we have couple of good news. One good news is finding eigenvectors when you have complex eigenvalues is much easier than the other two cases. Okay, and on the other hand, we only deal with 2 by 2 systems in this course, so that's much better than 3 by 3 cases, right? Okay, so let's get started. We have a differential equation and we have the matrix form for that, and we know the matrix A is then 1, negative 1, 1, 1. Now to find the eigenvalues, let's write A minus lambda I. So that means 1. So A minus lambda is 1 minus lambda minus 1, 1, 1 minus lambda. So we already know this. Now next thing what we do is we find the determinant of A minus lambda matrix and make it equal to 0, right? So let's find the determinant here. So the determinant is 1 minus lambda square. So we multiply these two, minus 1 times negative 1 is negative 1, right? So that's the determinant. This is equal to 0. Now we can write the same equation as 1 minus lambda square plus 1 is equal to 0. Now I'm going to expand this 1 minus lambda square, that because that's the way I like, and that what I get is lambda square plus 2 lambda, okay? Minus 2 lambda, my bad, minus 2 lambda plus 1 if you expand this, and here we have another plus 1 here. So altogether this is minus 2 lambda plus 2, right? So this is a quadratic equation because I always like to see my quadratic equation or the cubic equation in a 3 by 3 system. Okay, now you can use the quadratic formula. All right, so let's say we have found the roots for this characteristic polynomial as 1 plus or minus I. Okay, so we have complex roots, right? So our two eigenvalues are 1 plus I and the other eigenvalue is 1 minus I. Now do you see a relationship between these two eigenvalues? What do we call them? We call them complex conjugates, right? So these two eigenvalues are a complex conjugate. All right. Now let's get started and let's find the eigenvectors. Now here's the good thing. These two eigenvalues are complex conjugates. So the easy thing about finding eigenvectors for complex eigenvalues is that you only need to work with just the one eigenvalue. That means pick up the one that you like. Let's pick up 1 plus I. And just work with that eigenvalue. You don't have to find the eigenvector for the other eigenvalue. Okay, I will later tell you why. All right, so that's half of the workload, right, from the previous cases. All right, but the process is same, but be with me. Okay, I want to show you some new stuff. So new stuff is going on. So we want to find we want to solve the equation A minus lambda I times k is equal to 0. So A minus lambda I is actually 1 minus, now our lambda is 1 plus I, here negative 1, 1, 1 minus 1 plus I, right? So this is A minus lambda I. I'm just writing the A minus lambda I matrix without k. Now here I did something special. I use parentheses when I'm using my complex number, and you have to do that as well to avoid errors when you are calculating, when you are doing the subtraction, because we have to distribute this negative. So here this term will be like 1 minus 1 minus I. So 1 1 cancel out, here negative y, negative 1 1. Here this is 1 minus 1 minus I, right? So this is minus I. So this is A minus lambda I matrix in the blue color. So this times little k1 little k2 equal to 0 0. Now what we always do when we have 2 by 2 systems, we don't use Gaussian elimination. Okay, let's write the two equations. So let's multiply. Okay, so negative I k1 minus k2 is equal to 0. That's the first equation. And k1 minus I k2 is equal to 0. That's the second equation. Now we know for a fact that these two equations are the same equation, just a copy of each other, right? But do you see that here? Do you see that? Pause a minute and think whether the 1 or 2 are same. They are the same, okay? But the thing is that you don't explicitly see it clearly here like the previous two cases, like the distinct root and the repeated root case. Here actually equation 2, we can get the equation 2 by multiplying the first equation by I. Negative I times I is I times I is I square. So this is negative I square. I square is negative 1, and with this negative it's plus 1. That is why you have plus 1 here as the coefficient for equation 2 when you multiply equation 1 by I. On the other hand, negative 1 times I is negative I, right? So that is why you have negative I here. So these two are the same equations, okay? So don't worry. So we can work with the easiest one. What is the easiest one? Seems to be like this one, right? So k1 minus ik2 is equal to 0. So that means actually k1 is in fact ik2, right? If we take this term to the right. So let's choose an easy number for k2. What will be the easiest? 1, right? Let's choose 1. So k1 is I times 1, I. So the first capital K1, the eigenvector is I1. Now this is the eigenvector corresponding to the eigenvalue 1 plus I. Now notice your eigenvector is also complex. Okay, when you have complex numbers, you will get your eigenvector to be complex. So this is a complex eigenvector. Now we learn how to write this complex eigenvector as a real complex vector, like to identify alpha and beta version, vector version of the alpha and beta. So that will be like here 0 1, that is the real part, plus I 1 0, that's the imaginary part. This is the vector version of alpha, vector version of beta. So this is the eigenvector for rewritten in complex form. Okay, much clearer way. All right. So now this is the pair, the eigenvalue and the corresponding eigenvector. Okay. So now you may ask, well, we have another eigenvalue. That's the complex conjugate of the previous eigenvalue 1 minus I. So now the relationship is complex conjugates, the eigenvalues. So guess what? What is the eigenvector here? The complex conjugate of this eigenvector, right? That means 0 1 minus I 1 0. So you find a one eigenvector and for free you get the next eigenvector, right? See how much workload is released. Okay, in previous cases you have to do the process again and again, right? So in the complex case it's very easy. All right, so that is how you find eigenvalues and eigenvectors. Now let me end in this way. Even though it's a very good news, I have something to say to you. Really, when we want to solve the system of differential equations, now still we only found eigenvalues and eigenvectors, right? We didn't write down the final solution. Well, when we want to write the solution, really we don't use eigenvectors, the second eigenvector and the second eigenvalue. We only use a one eigenvalue, one part of the complex conjugate and the corresponding eigenvector. So really we don't get to use that advantage of finding the second eigenvector quickly. Okay, but still it's a huge workload less, right? So when we want to write the final solution for this differential equation, we only need a one eigenvalue and we only need its eigenvector. Okay, so how to learn the final solution? Well, that's a topic for a future video. Okay, all right, thank you.